I'm going to present a synchronization tool called Promise Plus that I developed along with my advisors, Ludovic, Henrio, and Matthieu. And Promise Plus allows, as the title suggests, a flexible synchronization for parallel computations on arrays. So first, a word on context. We are working in the field of high-performance computing, or HPC. And in this field, we usually find compute kernels. So a compute kernel is a compute-heavy operation like matrix multiplication, matrix inversion, or any combination thereof. And we are interested in composing kernels. So basically, the output of a kernel is used as input in another kernel. And usually, kernels manipulate arrays or matrices. And we are wondering about efficiency of the composition. And here, efficiency is tied to synchronization. If kernel A and kernel B are running in parallel, how does kernel B efficiently access elements produced by kernel A? Does it wait on each element? Does it wait on the whole array, on a chunk of the array? This is what we investigated. But before delving deeper into that, let's outline this talk. First, I'll present some common data communication tools that inspired us for Promise Plus. Then I'll present Promise Plus, which will be a bit technical. Then some talk about performance evaluation of Promise Plus, and then I'll conclude and present our future work. So, as the name Promise Plus suggests, Promise Plus is based on promises. A promise is a shared entity between two parallel entities, generally a producer and a consumer. It can be threads, processes, tasks, whatever. And a promise is tied to a memory location that will be shared between several entities. And it can be filled with an operation called set, and the value inside this memory location can be retrieved with an operation called get. And as we see here, get is a blocking operation. As long as there is no set, get will wait indefinitely. And as soon as set is performed, get unblocks and retrieves the value inside the promise. So a thing to note is that a promise cannot be set multiple times. You write a value once and you can't change it. If we look at combining an array and a promise, we only have two options: a promise of array or an array of promises. We can't have something that looks like a promise of chunks of array. That doesn't exist yet. So a second inspiration are FIFOs. So a FIFO is a queue in which entities can push elements and other entities can retrieve elements. Elements are retrieved in the order in which they have been added. You can add one element at a time and retrieve one element at a time, or you can add and retrieve several elements at a time. So there is already this idea of granularity. So things to note about FIFO: items are removed from the queue. So once they have been removed, they can't be accessed by somebody else unless transferred through another way. We have this idea of granularity with multiple items that can be added and removed at once. And we have no random access. Elements are read in the order in which they have been written. So where does all of that lead us? First, let's go back to efficient composition of compute kernels. As I said, there are three ways we can look at accessing elements in the shared array. Element-based synchronization, where kernel B will wait for every element in the array. Array-based synchronization, where kernel B will wait until kernel A has produced the whole array. And chunk-based synchronization, where kernel B could wait until a whole chunk has been produced. So we would slice the array preemptively, and an access to an element would wait until the whole chunk is ready. So this right here, element-based synchronization, means that kernel B will perform n synchronization, with n being the amount of elements in the array, which can lead to a lot of time spent synchronizing depending on the speed at which kernel A can produce the array. Array-based synchronization requires a single synchronization. However, this also means that there will be no parallelism between kernels. There will be parallelism inside kernels, if any, but kernel B will basically wait until kernel A has produced the whole array before starting. So this right here is not really interesting. And chunk-based synchronization, well, it's a bit of in the middle between both. We have less synchronization than with element-based synchronization, but still we can work before the whole array has been produced. And our intuition is that this will yield better performance than both other alternatives. And we created Promise Plus, a synchronization tool for matrices and arrays that integrates the notion of granularity of synchronization, this idea of synchronizing on a chunk. So let's look at Promise Plus. What do we want? First of all, we want an easy-to-use tool to share arrays between kernels, because nobody wants to use something that is complex. We also want an API that evokes arrays, so we'll use indices in this API. We also want some guarantees. For example, accessing an element in the array never produces an undefined value. This is similar to what happens with promises. When get unblocks on a promise, you are sure that you have a well-defined value, the one that was passed to set. And also, we want to have a sufficient unblocking condition. Any call to get can unblock under the right conditions. And finally, this is something that will differentiate us from FIFOs. We want to be able to access any element in the array any number of times and in any order. Compute kernels have no restriction whatsoever on the way they manipulate their input array. So let's look at Promise Plus. Promise Plus works very much like a promise. It even has a similar API. We have a set method that will take as parameter an index and a value, and a get method that will take as parameter an index and return a value. So both methods are rather intuitive. If I call set 652 on a Promise Plus, it will store value 52 at index 6 in an array that is held by the Promise Plus. And if I call get 0, then I will ask to retrieve value at index 0. So first thing to observe here is that Promise Plus will work also a bit like a FIFO, in the sense that values will be written in the order of indices. First, we'll write index 0, then index 1, then 2, 3, 4, 5, 6, and so on. This will be quite useful later. So here, A equal get 0. That's fine, but remember we are wondering about working with chunks. So where are the chunks? When do we unblock this call to get 0? Well, we will unblock every S calls to set, sorry. So what is S? When you instantiate a Promise Plus, you can give it a parameter, which we call S, or the step. And this step represents the length of a chunk in the array. So for example, here we have a Promise Plus with a step of 3. The array has been sliced in chunks of 3 elements. And if we want to access an element inside a chunk, we must wait until the whole chunk is filled. So for example, a call to get 1 will immediately produce value 10. But let's look at a call to get 3. If we call get 3, nothing happens yet, because this chunk here is not completely filled. We need to wait until index 5 as a value. So get 3 is waiting, and somehow in parallel we have a call to set 5 minus 23. This will write value minus 23 at index 5, and so the whole chunk is complete, and the call to get free unblocks producing value 47. Simple. So here on the left side, we have this big L. L is basically a value that indicates the maximum index that get can be called with that will unblock. Here, any value in the first chunk can be accessed immediately by get, so L is set to 2. Get 0, get 1, and get 2 unblock immediately. So you may be wondering, what happens if the array cannot be divided in chunks of length s? Well, let's look at what would happen if we have such an array. For example, here we have an array of 10 elements with a step of 3, and we call get9 in parallel with set9 76. We write 76 at index 9, but here, well, we have a chunk with 2 elements that are not filled, virtual elements in this case, but it doesn't matter. It is, in effect, a chunk, and it is unfilled, so get9 never unblocks. So our API exposes a third method, which is called setImmediate, that behaves exactly like set, except it will also trigger an unblocking forcibly. So now every call to get from index 0 up to index 9 included will unblock. So now that this is out of the way, let's talk about constraints, context, and guarantees. Promise Plus is to be used in a single producer context. This is a condition. We must have a single set per index. This is like promises. You can have only a single set on a promise. In Promise Plus, you can have a single set per index. And it works like a FIFO. Calls to set and setImmediate, abbreviated set I, are in index order. You can't skip any index. You can't have set 0, then set 2. You must have set 0, set 1, set 2. But we also have some guarantees. Get I never produces an undefined value. Get I is unblocked by a call to set j, with j in the range I plus s. And a corollary is that if all set up to I plus s have been performed, get I unblocks immediately. So here we have our sufficient condition for unblocking the call to get. And you may be wondering, well, what is the difference then with a FIFO? It's not maybe very clear. Well, the main difference between Promise Plus and a FIFO is the fact that elements are kept inside the array. You can access them multiple times and in any order, which is, when dealing with arrays, better than a FIFO that will destroy elements as they are read. And now let's talk about efficiency. So the main efficiency in Promise Plus comes from the fact that we have our step that allows us to have chunks of a different size. But that's not all. We also have efficient algorithms for get and set. So I talked about L, this value that indicates which call to get will unblock. It is an atomic value. It is shared between producer and consumers. But each consumer, as well as the producer, has a local version of L, which is a weak version. It is not atomic, and it is not always up to date. WC may not always be up to date with L, but it isn't its purpose. WC is here to perform optimistic checks. So let's look at this Promise Plus. We can divide it in four distinct sections: green, orange, red, and gray. The green section for this consumer is completely free of synchronization. WC is pointing to index 1, which means that call to get 0 and get 1 will unblock immediately. There is no need to check the value of L. Here, in the orange section, a call to get 2 or get 3 would have to perform a synchronization to read the value of L, which would in turn update WC. So here we can access values, but we will have to synchronize. The red section here, well, L is not yet here. we have not yet updated the last index. So a call to get here would have to wait until there are more calls to set before unlocking. And right here we have values that have not yet been set. So here again, we will have to wait. So you may have noticed that I talk about producer and consumers, multiple consumers. Each consumer has its own version of L, of weak L. So now let's move on to performance evaluation. So to evaluate the performance of Promise Plus, we wrote an algorithm that reproduces the dependencies of the NAS-LU benchmark. So NAS-LU is an algorithm in the NAS parallel benchmark suite. It performs a Gauss-Seidel iterative method on a 4D matrix. So our homemade algorithm has the same dependencies. It iterates over all non-boundary elements in a 4D matrix, and it updates each element based on surrounding elements. So the size of our test matrices was 24 billion elements. We run using 96 cores with 3 different matrix shapes. So a matrix shape means that all 3 matrices had the same amount of elements, but not the same dimensions. The objective was to have a different synchronization computation ratio. So here we have a graph, it's a graph representing the dependencies on a slice of the matrix, viewed as a 3D matrix. So basically, the idea of the algorithm is that you slice the matrix along these lines, right here, and you have a thread that will work on a slice. A thread here, a thread here, a thread here, and a thread here. Green arrows are dependencies that are internal to a thread. It is values that have been computed by this thread. Red arrows are dependencies between threads. So thread B right here in this chunk would have to wait for thread A to have produced this value until it can start working on this value. So we ran 2 different experiments with this. First, a comparison with classical synchronization. When Promise Plus is configured with a step of 1, it behaves like an array of premises. And when it is configured with a step of n being the size of the internal array, it behaves like a promise of array. So we are expecting the same time. And 2, computation time evolution as step evolves. So we started with a step of 1 and we went all the way up to a step of n being the length of the array, and checked how the runtime evolved. Here we have the code of the algorithm. So it is, as I said, it works on a 4D matrix, so we have 4 for loops. At the core of it is the update matrix function that will perform the computation part of the algorithm. And here, at the beginning and end of the second loop, we have the synchronization point. Here, this thread synchronizes with the previous thread to get access to value at index j. And right here, we signal the next thread in line that value at index j is ready. So you may notice that we discard the return value of get and we don't pass a value as parameter to set. This is because we had access to the global matrix, so we didn't need to actually put values inside the promise. We just needed the promise to act as an indicator of readiness. So here are the results. So here we compare the performance on the 3 matrix shapes between different synchronization patterns. So the blue pattern here is an array of C++ promises, which don't use atomics. They use a synchronization based on mutex and condition variables, which appears to induce a massive overhead in time. The green and blue are P plus max. P plus max is a promise plus configured with a maximum step, and P right angle brackets R is an optimized promise of array. optimized promise in the sense that they use atomics instead of mutex and condition variable. So these two patterns should behave roughly the same, and this is exactly what we get here, there, and there, with a small overhead for p plus max that can be explained by the fact that our synchronization is a bit more complex than just setting a Boolean value in the premise. And then we have p plus 1 in red and r right angle bracket p. So p plus 1 is a premise plus with a step of 1. R right angle bracket p is an array of optimized premises. Again, both patterns are expected to perform relatively the same, and it is actually the case right here, there, and there, with, once again, a small overhead for premise plus because of the synchronization technicity. And finally, in brown, we have p plus opt, opt being the best step we found for this particular shape of the matrix. So how we found it is coming right now. But either way, we see that there is indeed an optimum that exists. So now time for our second experiment. How does the average runtime evolve as the test step grows? So here we have a step of 1, or promise array of promise, and here we have a step of n, or promise of array. And we can clearly see that all three lines have a bell shape. Here we have a lot of synchronization, and here we spend a long time waiting. However, as the step grows, we spend less time in synchronization, and as it reduces, we spend less time waiting until somewhere along this line, where the step at 2 to the power of 8 gives the best result. And this is how we found this p plus opt. So some observation right here. I didn't talk about it before, but this synchronization right here is quite easy to write, and it is, in fact, really easy to achieve if we compare it to what happened in the original code in the NAS parallel benchmark. Here and there, we had two calls to synchronization functions that performed an alternate bit synchronization that we basically replaced with a call to get for one and a call to set for the other. The second thing to note is that we didn't change hardware or anything. Everything we have here was performed with the same hardware as for the NAS parallel benchmark test. So we have an increase in performance without changing hardware. So let's conclude. First, some related work that inspired us. First, we have WeakRB. WeakRB is a correct and efficient bounded FIFO queue that uses atomics for efficiency. It has support for bulk insertion and removal. So this is where we took some of our ideas. It works in a single producer, single consumer context because values are removed from the FIFO as they are read. So in Promise Plus, the FIFO is not consumed, the array is not consumed, and it allows us to have a single producer, multiple consumer context with, however, a heavier memory footprint. OpenStream is an extension to the OpenMP threading framework that adds streaming to OpenMP. It has support for granularity of synchronization. An OpenMP task can now wait until a given amount of elements are available in a stream before starting. It works in a single producer, multiple consumer context. Several tasks can consume the same stream. But to do that, OpenStream enforces an order of execution on OpenMP tasks, and values are removed from the stream as they are read. So once again, Promise Plus doesn't remove values from the stream and is not bound to a specific threading framework. So in conclusion, we proposed Promise Plus, a tool that allows synchronization on slices of arrays between tasks, arrays or matrices. It has a configurable granularity with the step. It can express different synchronization patterns, promise of array, array of promise, something, something, promise chunks. It improves performance with an extensive code refactor or changes in hardware sometimes. It has the same guarantee as the classical promises. A call to get never produces an undefined value. And we have a simple sufficient condition such that get unblocks. So where are we going from here? We are working on dynamic analysis that would optimize the step automatically at runtime. So the programmer would just have to focus on where to put synchronization points. And we are searching other applications that would benefit from Promise Plus or from a synchronization akin to what we do in Promise Plus. Thank you all for listening, and if you have any question, I'll gladly answer them.
Thank you very much, Amaury, for the interesting talk. We have a couple of minutes for discussions. I still do not see any questions posted in the chat box. So about the index order in setting, I mean, it's good for when you are getting values, you can do any like order. But what happens is I didn't get if you jump some of the undefined values and goes and set a value later. So would it be a problem with your blocking, or what is the problem that you have this constraint?
Okay, so for example, let's look at this Promise Plus. If I skip index 5 and I call set 6 with something, internally the Promise Plus will think that, oh, there has been a call to set 6, and the last index that is readily accessible is 2. 6 minus 2 is 4, which is greater than the steps. So, well, I'm going to set L is now 6, and a call to get 5 could be allowed to unblock immediately, even if there is no value set for index 5. So we could, in this case, have a get that produces an undefined value, which is something we want to avoid. Does it answer the question?
Yeah. For the, I mean, one of the goals of this project you said is to ease the programmer interaction. So, are you planning to make it even easier by like removing some of those details that the programmer have to specify? Like, I guess you showed some conditions on one of your slides that. Yeah, for example, set immediate and things like that. Can you synthesize them automatically, or I mean, do you have any future work to make things easier, or how does it work?
Right now, we don't have plans to make things easier. Regarding set immediate, I guess we could probably say that once the last value in the Promise Plus is written, we could automatically unblock. However, there is a little something I didn't say about set immediate, my mistakes. One can use set immediate not only to set the last value in the Promise Plus, but we can also use it anytime, in fact. For example, if the programmer knows that at around index, for example, 42, it would be interesting to unblock and not wait until the whole chunk has been produced, the programmer can call set immediate with 42 as index to immediately unblock everything before index 42. So it can be used as a force unblock anywhere in the Promise Plus, although this is not necessarily the first thing we wanted when we added set immediate.